Right. The quality of a thermal response test. In the previous graph, we saw really ideal test data, let's say, but often not every test is perfect, and often we have some kind of problem, or sometimes we have some kind of problem. For instance, here we can see that the control of the power injection was not able to keep it really constant, and we get all these oscillations in the blue line, which are pretty wide. So this is one problem we can have, the heat rate not being constant or oscillating. This can be due to, for instance, the electrical grid having a higher load on it during the week and lower load in the weekends. Then if the electricity, if our test does not control it properly, the power input will vary with time, or we can have a control issue that causes these type of oscillations. Other effects that are possible are effects of ambient temperature. Being low at night and high during the day, for instance, and not well insulated connections to the borehole. Effect of groundwater flow, which will completely invalidate the results because conductivity is not, or heat conduction is not the only process anymore of heat transport in the ground. And we can have effects of rainwater infiltration, for instance. Now, there are some solutions. We can, for instance, in the case here, filter the data or use the return temperature and not the injection temperature, because the return temperature is much more stable. We can use the recovery period. So after we turn the test off, the temperature will, let's say, recover to the natural temperature. Then we won't have any issues with control or grid from power grid anymore. And we can try to analyze that part of the data. We can use different models, alternative models, for instance, models including groundwater flow or adjusting for ambient temperature to get a better estimate of the thermal conductivity, taking into account other processes that occur. And of course, it is always possible to retest. That means that you have to do the evaluation of the test data before you remove your thermal response test away from the location. And you can wait for a couple of hours or a couple of days and do a further new test on the same borehole. It is, in any case, always important to check for your assumptions, check for your fundamental assumptions, and also check the quality of the data that you have obtained. We need a constant heat rate. We assume that conduction is the heat transport mechanism, so no groundwater flow, and also we should not have any convection in the borehole. On the right, you can see a graph where we look at the constancy of the regression results. So we take a little bit of data, adding data to it, and see if the value of thermal conductivity stabilizes in time. If this is the case, we hope that we have a good result. An error analysis can be carried out, looking at this constancy of regression, but also taking a look at the error calculation with all error sources included. Here is the reference and some idea of the different sources of error that we can take into account. For instance, the heat injection rate, but also the density of the fluid, the error on the temperature measurements, the measured height of the borehole, etc., etc. The validation of the method has been carried out. For instance, in 2002, we published a test result where we had very detailed data on the soil profile. We had samples of the soil profile which could be tested in the laboratory, and we did a thermal response test on the same borehole, compared the values that we obtained from the laboratory with the values from the field, and you can see that they were very close together. The field value 2.13 and the lab and soil profile 2.097.